Good morning, ladies and gentlemen. Today we are starting a new unit that focuses on magnetism, okay? And today we're going to start with section 1, which focuses on magnets and the magnetic field, okay? Here, start this off with a prompt. I'm sure you guys have all worked with magnets before, but do you understand why it is that they're magnetized in the first place, okay? Let's go through this prompt real quick. So, we have an iron nail and we have an iron magnet. Okay. The iron nail can be attached to the magnet, but it can't be attached to the other nail. Okay. But two magnets can attract each other. So what they're asking us is either end of the nail attracted to either end of the magnet. Okay, we know that magnets have poles, right? There's a north pole and there's a south pole. If we had a magnet and we had a nail, can the nail stick on either end? The answer is yes, they can. Is either end of the magnet attracted to either end of the other magnet? If you've experimented with magnets before, you know that they can repel each other and they can also attract. Like electricity, where you had positive and negative charges, like charges repel and opposites attract. Same thing with magnets. If you have opposite poles, north and south, they attract. If you have the same poles, they repel. Okay? Now, these next two questions are what we're going to be learning about. Both the nail and the magnet are made out of iron, but why is one magnetized and the other is not? Okay, what happens when what happens when we bring the nail to the magnet and it sticks? Because if you bring two nails together, they don't stick, but the nail sticks to the magnet. Why? So, anything that can be magnetized or is a magnet is considered to be a ferromagnetic material. Ferromagnetic materials are materials that can be magnetized. Okay, things can be magnetized, they can also be demagnetized. I don't know if you guys have ever dropped your I don't know if you have refrigerator magnets in the first place. Not everyone has refrigerator magnets, but let's take a refrigerator magnet as an example. If you drop a refrigerator magnet enough times, it will eventually stop working. Okay, it will no longer be a magnet. Eventually it does, the effects go away from dropping it. Dropping it can damage magnets. Okay, and as we said before, magnets have two poles. They have the north and the south. Opposites attract and like poles repel. And when magnets are free to rotate, like a compass, that's what a compass is. That little arrow in the middle is a magnet and it spins on the thing in the middle. When they're free to rotate, the north pole points towards north. Okay? So, why are things magnetized? There are these things called magnetic domains. Okay? These arrows, think of these arrows. These arrows are magnetic domains. When they point in random directions like this, like in here, they're pointing in random directions. When they point in random directions, the material is not magnetized. Okay, this is like any metal. Okay, so paperclip, you can any random metal, the nail, the paperclip. This is what it looks like. This is what the magnetic domains look like. Inside a magnet, these arrows all point in the same direction. Okay, when these arrows all point in the same direction, you have magnetic alignment, and now the material can produce a magnetic field. Okay. So the question here was both of them are made of iron, but why does the magnet behave differently? The reason the magnet behaves differently is because the iron magnet has the magnetic domains aligned. The iron nail does not. Okay. The iron nail does not. That's why they behave differently. They align the domains in the magnet in order to make it a magnet. Okay. And that's why it sticks. And then the bottom one, what happens to the nail when we bring it near the magnet? Okay. Once you have one magnet, you can use that magnet to create other magnets. Okay. So because iron is a ferromagnetic material, That means it has magnetic domains that can be aligned. Okay, so when you bring the nail to the magnet, what happens is these arrows inside the nail temporarily become aligned. And so when they temporarily become aligned, now the iron nail temporarily becomes a magnet. And that's why it sticks to the magnet. Okay. So when you pick up something with a magnet, what the magnet is doing is transforming the thing that's sticking to it into a magnet as well, because that's the only way it would stick. Because as we said here, opposite poles attract. Okay. So what it does is that it makes the material the opposite pole on whatever side you stuck it to, and then it sticks to the magnet. Okay. That is what's happening. If you wanted to make something else a permanent magnet, you can do the following. Okay. And you guys actually may have seen this before. So let's say we take this paper clip. Okay. The paper clip is not magnetized. But let's say we take the paper clip and we bring it to the magnet. When you bring it to the magnet, it'll stick. But if you rub the paper clip on the magnet over and over again, if you rub the magnet or rub the paper clip on the magnet over and over again, eventually the domains, these arrows, will start to align themselves in one particular direction. And when that happens, you would transform the paper clip into a magnet. And you can use that paper clip to pick up other stuff. Now, it wouldn't remain that way forever. Eventually, the paper clip would become a normal paper clip again, but you can make it into a temporary magnet. Okay. So, the only things that can be made into magnets, just to review, are ferromagnetic materials. Okay. Those are the things that can be made into magnets. And what makes them into magnets is the alignment of these magnetic domains. Okay, that's what makes them magnets. Okay, and by dropping magnets, that shock can move these arrows out of alignment. And that's why if you drop a magnet enough times, it'll stop working because you will have destroyed the alignment. Okay, and now it's no longer magnetized. That's why dropping magnets does that. Okay. Now let's start talking about magnetic fields themselves, okay? So here they're talking about how do we detect fields? Well, how do we know that there's a gravity field around us? Well, if things are falling, we're all, none of us are floating, right? None of us are floating. We're not magically floating. So that's how we know that gravity is present. That's how we detect the gravitational field. What about an electric field? How do we find an electric field? Well, if you have a charged particle, that charged particle will move if there's an electric field. So that's how you test that. And then how do we test for a magnetic field? Well, commonly we use a compass. Okay. If you have a compass and the compass is moving around, then you know you're inside a magnetic field. And guess what? The Earth is surrounded by a gigantic magnetic field, and that magnetic field is keeping us alive. Okay. It protects us from radiation. What do these magnetic fields look like? They look like this. Okay. Just how with the particles, where we had things coming out of things go out of positive charges and go into negative. Here, note the direction of the arrows. It always goes out of north, okay, and it comes into south. Okay, notice the direction of the arrows. It comes out of the north and into the south. And this is what the field lines actually look like. This is not made up stuff. This is what they actually look like. And I'll show you right now with the video. This is a demo that we would actually do in class, but unfortunately, with everything going on, we can't. But this will show you, this is going to prove that those lines are actually legit. So if you have a magnet and what he's pouring is iron, okay, those are iron fillings. If you pour the iron fillings on the magnet, you can see the field lines, okay? That is what they actually look like. It goes out of the north and into the south, okay? Those field lines, this is actually what they look like, okay? So these arrows, these aren't just made up, okay? This is what the field actually looks like. And remember with the compass needle shows the direction of the field, okay? It goes out of the north and into the south, okay? So when you have a compass, the compass, what it does is it follows those lines, okay? That's what the compass wants to do. And the spacing is another way to represent the strength of the field. The closer the lines are together, the stronger the field, okay? Notice that the closer you are to the magnet, let's talk about this gap. Look at this gap. Okay? The closer you get to the magnet, the smaller the gap gets. The further away you get, notice how the gap gets bigger. The bigger the gap, the weaker the field is in that area. Okay, that's just one way to represent it. Where are the lines closest to each other? They're closest to each other at the ends. Okay, that's why the ends of the magnets are the strongest. Okay, this is where the magnetic field is strongest, at the end of the magnets. Okay, so that's the magnetic field. And then there's this thing called magnetic flux. Okay, magnetic flux is just another way to quantify the strength of the field. What it is, it's the number of field lines passing through a particular area. And by field lines, again, they're referring to these arrows, okay? So how many of those arrows are passing through a particular section in a particular amount of time? That is magnetic flux, okay? I'm going to hold off on this equation for now, okay, as it involves having to calculate angles and tangent and cosines and things like that, okay? I'm not going to focus on that for now. I told you that I was going to make the concepts the priority for now. So for now, I'm going to do exactly that. Let's focus on the concepts, but just know that magnetic flux is another way to represent the strength of the field, okay? Then you have Earth's magnetic field, okay? When you have a compass, okay, the north pole of that compass is going to either point technically to the north or the south side. It can point to either direction. Why do I say that? It's because Earth's poles actually switch around from time to time, okay? I forget how often it happens, but the North Pole, for example, isn't necessarily the magnetic North Pole, okay? You have what they call geographical north and you have magnetic north, okay? The North Pole is on the north side of the Earth, but that does not necessarily mean that the magnetic north is in that same location, okay? The North Pole and the South Pole of the magnets can actually change sides from time to time, okay? And that can happen, and that's you have to know that if you're going to use a compass, because that does affect how compasses work, okay? But this is Earth's magnetic field. The magnetic field comes from the iron in the core, okay? At the core of the Earth is molten iron, okay? And the Earth spinning, that spin churns everything around and produces a magnetic field. And that magnetic field is what protects us from radiation, okay? And these little prompts I'm not too concerned about. And that is the end of the magnetism section, okay? So key things to highlight that I want to highlight, the most important parts of this is ferromagnetic materials are what can be magnetized. If something is not ferromagnetic, that means it cannot be made into a magnet. You may or may not have already known this, but not all metals can be magnetized, okay? Not all metals will stick to a magnet, okay? So you have to have a ferromagnetic material. And then the second biggest highlight is this, okay? Magnetic domains. These are what produce the magnets. If they are aligned, you have a magnet. If they're not, then you don't. You can temporarily align them with other magnets. So you can make more magnets from one magnet because you can use that magnet to align the domains. And dropping magnets can break them because it knocks the alignment out and gets rid of the magnetic fields. Okay, those are the key highlights for today. Okay, today for the work portion, there is a study guide with, I believe, 3 questions on it that I would like you to go through. Because there's very few questions, I want you to try to go through it on your own. You guys can do it, Okay, so I will leave that to you. Okay, I won't go through an example of that. But today, just I want to focus on the concepts. All right, that's what I'm trying my best to do here. I know we previously talked about the math getting out of hand at times, and it can get a little complicated. I'm trying to focus on the concepts. But that's it for today, ladies and gentlemen. Hope you guys are doing okay. Take care and enjoy the rest of you.